a minute. I will. It should have gone live and it hasn't. I take it back. Sorry, I apologize. There it is. It's running now, I think.
Okay, that's great. Sorry to interrupt.
No problem. Yeah. So yeah, as I said, T coronavirus. So it has short-term sort of twinklings as well as longer-term ones, and that's the sort of picture of a nova with a red giant and a white dwarf, where materials transferred from one to the other. And this is a longer-term light curve. So there are longer-term variations as well. These are periods of about 100 days or so. And then when the nova finally erupts again, it will be much, much brighter, going from about magnitude 10 to magnitude 3. So we obviously want to be the ones to capture that, but I think when it goes, it'll be so obvious, a lot of people around the world will capture that. And finally, this is one of the most recent images that we took of M51. And I think this is just amazing data that numeral telescopes have been able to capture. And this was processed by Eros Tang, and I think that's beautiful, amazing data. So our observatory is doing really well. Still a few things to finalize and tweak, but we are getting there. I just thought I'd give you some reminders for members, really. If you haven't been on our members website, it is you need to log in for that, but you all should have that. And if you haven't, just let me know. But there's lots of information available. All our recent newsletters are there, and access to our Azero page, where you'll find all the information you need about the observatory there, and various links, and also a button to request that we observe something for you. So click on the Azero request form. You can fill in all the details as much as you can. Why you want to do it, what it is, when's the best time to observe it, and so on. We're always looking for things to observe. We have lots of time available to us, and it's better that we have things planned than getting to the start of the evening and think, what should we look at now? So there you go. We also have information on our comet projects. All the results get posted there, and the latest images, as well as our variable star project and one or two other projects as well, such as the asteroid project. So if you remember, that's where you can find out all the things that are going on. Okay, finally, the talks over the next couple of months. On the 3rd of May, we have an introduction to cosmology with JWST from Gary Fowles. That started to happen last year, but for various technical reasons, it had to be stopped, and we will do that on the 3rd of May again. I believe Gary will be with us in person this time. So that will be at the Augusta United Church in Edinburgh, as well as on Zoom for members and YouTube for visitors. On the 8th of May, we'll have our usual Imaging and Observing Group meeting. That's online on the Zoom for members. On the 17th of May, we have an online-only talk from Jared Gilligan about William Lassell, telescope, planets, and drinking beer, which we all like to do, of course. And on the 7th of June, we'll have a talk about dark energy and matter. The titles to be confirmed on that one from Professor Andy Taylor, and that will also be our AGM. Okay, well, that's it from me. I'm going to stop the share, and I'm going to hand you over to Sandra Brantingham, who's going to tell us about the secret life of stars. So over to you, Sandra.
The mute, go to share screen. Okay, have you got that?
We've got that. That's great.
Excellent. Right. Hello, where are you? That's it. Right. Okay. Quick adverts first. This is my job. I've been doing that since 2016. And British Astronomical Association. I've been doing this since 2008. Society of Popular Astronomy. Same job. So that's what I do. So the road to the stars. What am I going to cover? I'm going to cover what we've discovered, why there are different stars, how they work, and where we come from. It jumps about a bit because of the way it works, but I'll try and cover everything. And also, if you've got any questions at the end, please ask away. You know, the one thing I do like is that A, there's no such thing as a stupid question in astronomy, and B, ask as many questions as you want. So here we go. The history. Uh, Astronomy is the oldest science. People sometimes come up to me and say, "Why astronomy?" I said, "Well, it controls all of your life, whether you realize it or not. Controls the seasons, controls when you get up and go sleep. Um, it controls the length of the year. Um, it does just about everything. It makes everything change. And if you look around you, you'll see that your walls are made out of concrete and not tents. The reason we do that is because we can farm. And if we farm, we stay in the same place. If we stay in the same place, then we've got to know what the weather's going to do. And the weather is controlled by the seasons, and the seasons are controlled by astronomy. So knowing astronomy teaches you how to grow and when to grow, which is very important. So that's why it's the oldest science. Um, of course, up there, it's magical stuff, so it's all gods and spirits. Um, there shapes of heroes and animals. Every one of us, I think, when we were young, joined dots and stuff like that. So it's automatic when you see stars to say, "Oh, that looks like that," or "That looks like a crab," or a lion, and things like that. And so that all came from it. And it's also, once you do that, it's easy to remember them. Uh, they were described as holes in the curtain of night. Um, there was one exception. There was a guy in Greece, and I forget his name. He said maybe, just maybe, there's suns, but far away. Um, and everybody laughed, which is a clue. If somebody laughs, it means A, they don't know, and B, you're probably right. But that's something that we'll cover later on as well. So what can we look at as stars? Well, there's three things we can look at: how bright it is, or its magnitude; dark lines, and I'll cover that in much greater detail; and color. So those are three things that differentiate stars. Magnitude, or how bright. Hipparchus was the first guy to make any headway in this, and he said, right, the brightest one is 1, and the weakest one is 6. This caused a bit of confusion, but you'll see why in a minute. Pogson decided that between 1 and 6 there was 100 times power. Now that was all right, but if you get a brighter than 1, it goes minus. So this is where it's not intuitive. For instance, the sun is minus 26, so it's really, really bright. 6 is about the limit of our eyes, and most of us use the plough and bits of the Ursa Minor to figure out the seeing. So you get one's very bright, and if you can see all of Ursa Minor, then you've got really good seeing. This is known as apparent brightness. In other words, it's apparent to you. You look up at stars, that's great. Now, absolute brightness I'm going to cover in detail later, but this is what it means. It's an equal comparison of all stars. It's done at 10 parsecs, which is 32.26 light years, and it shows us there's a vast variation in the brightness of stars. How we got there is quite an interesting story, and I'll cover it later. Right, next one. Anybody recognize this gentleman? Sir Isaac Newton. He was the first to realize that light split into colors when it passed through a prism. He was the start of that. And even though he did gravity, he thought this was one of his greatest discoveries. He thought it was amazing that light was made up of all these different colors. And it was. We'll go much later now. What we take for granted now is probably nearly everybody I'm talking to there has a telescope, or 2 or 3, like me. Back then, you only had a telescope if A, you were very, very rich, i.e. a lord or something like that. Probably the fifth son, so no inheritance. You were paid by the king, or you were like this guy. You did glass. You can make one. So otherwise, they cost a fortune. The British were the best glass makers until this guy came along, Joseph von Fraunhofer. He was an absolute genius, and he began playing with glass in ways that nobody had ever thought of. He invented the spectroscope, and he managed to discover 574 dark lines emanating from the sun. It was really clever. He also invented the diffraction grating. Now, some people say if you get a CD, well, you can always do this. Get a CD and hold it so the light bounces off, and you'll see all the colors, and that's how a diffraction grating works. Some people say they can even see the dark lines. I can't, so I'll give up. So, but basically, this is a basic solar spectrum with all the dark lines that they discovered, and this is the sort of machine you can get to do it. And if you've got several £100,000, you can get something like that. If you haven't, you can get something like this, and it really does work. It only costs you about £7.45. Bit of advice when you're putting it together: the lens is A, tiny, and B, you can't get any glue on it. So you got to, but it does work, and you can see the frequencies of the lines through it. I didn't point mine at the sun. I pointed it at a white wall, but I got out H1 hydrogen alpha straight away. So it really does work, and it's nice and cheap. They've also got all sorts of other bits and pieces, astronomical stuff, but for a nice cheap one and getting kids into it and things like that, brilliant. So what happened next? Well, they've discovered these lines. They burnt chemicals in the lab to find out what lines they caused. They burnt all sorts of things. They even burnt diamonds, would you believe, to prove that they were carbon. So, and all these Biohofer lines, told them what they were. There was one set of lines they had no idea what it was. So they called it Helios. Helios is the Greek name for the sun. We now call it helium. So it was discovered first on the sun. Interestingly, it was also discovered decades later in the 1920s in rocks in the United States. And they started to mine it and sort of produce it. And guess who was interested in it? Nazi Germany wanted it for their airships because, unlike hydrogen, it doesn't blow up. Very wisely, the Americans refused to sell them. But that's why helium is wrongly named, because it was first discovered on the sun. They looked at other light sources, and then they looked at stars. Now, up to this point, the sun was the sun and stars were stars. Some people thought they were the same thing, but this proved it. And the sun is a star, and the stars are suns. And it was the first time that this had been proved conclusively. The sun is a star because it's big. I'll get into a bit later, but most people don't understand this, how big it is. If you're doing this talk and you've got kids involved, with 100 sheets of paper, it works brilliantly. You get 3 volunteers, and what you do is you say, how big do you think the sun is? And they say, 100%, oh, 50, 60, 70, 80. You end up giving 99 to the one that's playing the sun. You have one playing Jupiter, and you take the last sheet of paper and you tear it half and give half to the sun. So that's 99.5. And then you tear the next sheet of paper, the one remaining sheet of paper in half again and give it to the sun. So that's 99.75 or 7.75. And then you fold the last piece into 3 and you tear one bit off and give it to the sun. So 99.86, and the mass of the solar system is the sun. It's a monster. It's absolutely huge. What's left, you tear slightly to the right of the center line, and that's Jupiter. Excuse me. Proving that Jupiter is bigger than everything else combined in the solar system. If you got everything, shoved it all together, you wouldn't make another Jupiter. So how big's Earth? Well, you take a bit about the quarter of the size of the thumbnail and tear it off what's left of the last piece of paper, and that's the size of the Earth. Um, it's it's 320 Jupiter's 320 times bigger than the Earth, so we are absolutely tiny. So just a quick guide to how big everything is. There's little Pluto, Mercury, Mars. Venus about the same size as Earth, so there's Pluto now, tiny little dot. The gas giants are the big ones, Neptune, Uranus, Saturn, and there's Jupiter. Think those are big. That's it. There's the sun. There's Earth right down there. That's where we stand. That's how we stand. So if this thing does anything violent, we've got problems. For those who think the sun's big, there's the sun. There's down. You find that's the one on the left, with Pollux and Castor in the Gemini of the twins. Oh, I've just been told my internet's unstable. One or two. Arcturus, that's the one. If you follow the handle of the plough all the way down, bottom of Bootes the herdsman, it's known as the bear keeper. There's the sun, a pixel. There's Sirius, Pollux, and Arcturus. Rigel, bottom right of Orion. Aldebaran, the eye of the bull. Betelgeuse, top left. And Antares, the eye of the scorpion. Well, the center of the scorpion. If Antares was where the sun was, we would probably be in its sizes. Right. Color. Since the Iron Age, has been known that metals glow with different colors and different temperatures. So, and most of you have looked different one. So by comparing the colors, the magnitude, and the dark lines, which become the many different types of suns, but these could be classified. So how did we classify them? So this is how basically how it works, and it's basically surface temperature going down. And I'll just go through this quickly. There you go. And now you've got here, oh, be a fine girl, kiss me. Now, you might think that's a bit sexist in these modern days, but the mnemonic was invented by a lovely lady called Annie Jump Cannon. She worked on these stars, and she was one of these girls. I didn't realize until a few years ago that she was partially deaf. Now, you talk to a doctor, and they'll tell you if you lose one of your main sensors, the other sensors take over, and her sight was incredible. And she could say, that's an A3 or that's an A4 and things like that. So she worked hard on the classifications. There they are. Each one is spread into 1 to 9, and the sun, we're G2. There you are. And with temperatures on the sun is about 5,800. But there you go. That's about the standard. So there's the classification. So we managed to classify them. We've got the dark lines and stuff like that. What are we short of? Well, we're short of how far something is away. What's a parsec? Right. If I stand up and spin round, I'll go through 360 degrees. If I hold my arm up and bring it down, 90 degrees. If I hold my little finger out just at the end there, from me, that's about a degree. And the idea was that the Earth is 150 million kilometers from the sun. In 6 months' time, it'll be 150 million kilometers from the sun on the other side. So that gives you a baseline of 300 million kilometers. And so you can triangulate. Brilliant idea. Right, let's give it a go. So they tried a degree. That didn't get them very far. Now, a degree can be split up into minutes. To differentiate them, they're called arc minutes. And as per an hour, there's 60 arc minutes in a degree. If you do navigation, you'll also know that an arc minute is equal to 1 nautical mile on a map on a great circle. So very useful for navigation. They tried that. That didn't work. Well, an arc minute can be split into 60, and guess what it called? Seconds. Yes, arc seconds. And they tried an arc second, and that got them. So measure the angle of the star, measure it again 6 months' time. If you get a difference of 1 second, an R is 1 parsec away, 3.6 light years. And everybody shows this as a triangle, but it doesn't look like that at all. What it looks like is a dot, which will represent the entire solar system, a line, and another dot, which represents 3.26 light years. If you look very closely at the line, you'll see that there's 2 lines there, but they're parallel. Now, the first 3 letters of parallel are PAR, and the first 3 letters of SEC are SEC, and that's where the word came from. And if you remember that, you'll also have an answer for some of the questions that come up on University Challenge or Mastermind and things like that, because it's been asked several times. And that's why a parsec is used. Brilliant. Yeah. So a second of an arc is tiny, you know. Next problem. The next problem is, well, it sounds difficult. All this is the nearest star to our sun is Proxima Centauri in the Alpha Centauri group, and that's 4.2 light years away. So all stars, and I mean all stars, have a movement of less than 1 arc second. So when they show this thing on the television and say in parallax and see the star jumping back and forward, what they fail to tell you is it's multiplied by thousands of times to see it jumping like that. It sounds very difficult, and it was. It was a very difficult thing to do, and yet, they managed to crack the distances of 150 stars. Very hard work, a lot of photographing involved. And this is in the days of plate cameras and things like that. So, but they cracked 150 stars. Oops, just need a quick swig. So now there's a couple of guys called Hertzsprung and Russell, and thought, what we're going to do with this? We'll make a diagram. Right now, everybody looks at this, go, oh my God, so don't understand it at all. Pretend there's nothing on it, right? And what they've done, and they've calculated the absolute magnitudes of what they did. Now that they knew the magnitude of these 150 stars, if I look at the screen down here and I've got all these pictures of people, I've got heads of different sizes, but I've no idea who's the biggest and who's the smallest. So the only way I could do that is to get you all stand at the same distance. And that's what they did. They stuck everything at 10 parsecs and just used the inverse square law to do that. So they could then compare all the sizes of the stars. And they started plotting them. And they were going all there. And then they went, oh my God, run naked down the street or throw papers in the air or bits and pieces like that, or cracked open a bottle of wine as you do, because they suddenly realized that all the A's and all the B's and all the O's were all together. In other words, plus or minus a little bit, and we all know there's a bit of error in these calculations. An A3 produced the same light. So all you had to do was to identify an A3, find out what it's like, compare it with what you got from an three on here. It's distance. In other words, this is where it all started to expand out. Later on, we began to realize that we were looking at a forest. And you had the saplings here, you had the really old ones here, you had the really big ones and bright ones here. In other words, you were looking at the right mixture of ages and sizes. When I was giving this to my group in Huntley, I was saying, this is where all the giants go, and they go when they die. And the lass says, "Oh no, that's Cemetery Lane." You know, I said, well, they didn't call it that, but yeah, you're about right. So that's where all this started. We learned a lot more from it, but it initially gave us a big kick to finding out the distance of stars. So the next one was the Doppler effect. Here he is, and he's been my friend in work as well for the past 40, 50 years. This is Hans Christian Doppler. Some stars had the same lines, but in different places. And he theorized that as the same stars came towards us, they increased or blue shifted. And as they moved away, they decreased or red shifted. He then did something very, very clever. He predicted this would enable astronomers to chart the furthest stars. What he didn't know, it was now chart the furthest galaxies. So very, very clever. Very, very clever. Another problem. Some stars didn't seem to have lines that belong to that type. There's a classic one. I'm already seen Pollux. If you remember politically correct, you remember Pollux and Castor at the top of Gemini. Well, Castor, when we got the telescope on it, had 3 stars. Then we got the black lines, and they thought, whoa, each one of them had another star. There were multiple stars, but you couldn't see them. In other words, Castor is 6 stars. So lovers of Star Wars and Tatooine with 2 stars. And imagine a planet up there, and you've got 6 stars in it. There's another problem. Dust and gas gets in the way, but this was the star. This is where we all kicked off, and now, of course, we've got standard candles, we've got Wolf-Raynaud stars, but this is where it started. Okay, so how do suns work? There's 3 things that affect sun's atoms: gravity, nuclear fusion, and magnetic fields. So gravity, it pushes all the atoms together. It raises the core temperature, and that's why a sun has to be big. It has to have a massive core temperature, and it has to have it to start nuclear fusion. So what's nuclear fusion? Now the funny thing is, I was watching the program on the nuclear bomb experiments and things like that, and all the bits and pieces that go together. And I began to realize that 100 years ago, nobody knew anything about this. What, 80 years ago, a handful of people now can teach nuclear fusion to cubs. So, and it's very, very simple. You've got to understand the hydrogen atom. And the hydrogen atom has 1 proton, which is big, 1 electron, which is 1,836 times smaller, but it balances and it orbits the proton. Now, oops. Right. Oh, right. So that's the hydrogen atom. Now, this is the sad part of the story. To put it in perspective, at the time this last was about, everybody thought that if they made the Earth bigger and bigger and bigger, it would become a sun. She said, no, that's not correct. And she discovered that sun was mainly made of hydrogen. In fact, nearly all suns are made of hydrogen, and that's how they work. Unfortunately, she was forced to to, shall we say, put a disclaimer in, which is again a warning if anybody's writing papers. If you think you've got it right and you've peer tested it and people say, oh, that's not the way we think, stick to your guns. If she'd stuck to her guns, we'd learned a lot faster, but she was poo-pooed. But now she's revered as one of the cleverest girls going. Celia was a very, very sharp young lady. So, nuclear fusion. It makes 4 hydrogen atoms into 1 helium atom. 2 electrons and 2 neutrinos are left over. Neutrinos are the funniest things I've ever come across. When the first thing to use to detect them, they went down a mine shaft. I think it was in Canada. Deepest one they could find is in Canada or South Africa. Dug a huge hole the size of a swimming pool, covered it in sensors, and filled it with dry cleaning fluid. And that was to detect neutrinos coming through from the other side of the planet. Weird ones. They've got one in Antarctica now, which is below the ice, again to detect stuff coming through from the other side of the planet. Once they take off, neutrinos go through everything. There's also 3 phases of them, 3 states of them, and there was a big panic when they thought, oh, it's not getting enough. Then we suddenly realized that they keep changing states. Why they change states, we don't know yet. So that's part of the fun. It's the 2 electrons that give the power of the sun. You might not think that's much, but when you consider that the sun burns about 750 million tons of hydrogen and converts it into helium every second, then you get the idea. There's a lot of electrons coming. In fact, it's about 10 to the 39 that created. They bounce all over the place until they get to the surface. Then they come charging off as a solar wind, and tonight you should be able to see them as the aurora. So there you go. The sun will live for about 10 billion years. It's been going for about 4.5 billion years so far. It's got another 5 to go. Then it'll expand into a red giant, eat us all up, and then it'll go into a white dwarf. By then, we'll probably, well, the way we're going, we'll be extinct within the next couple of years, but that's the plan anyway. That's the long-term plan. At 5 times the sun, it lasts for about 10 million years. The core temperature is sufficiently high to burn helium into carbon, and then it goes up through all the different bits and pieces. All those are exothermic. In other words, a really, really hot sun. This is a rough idea of what we think a star looks like just before it blows as a supernova, because that's what happens next. So the bigger the star is, the hotter it burns. Size is really the hotter it burns, the brighter it is. The hotter it burns, the shorter its life is. There are some red dwarfs that are going to live for trillions of years, not billions of years, but the hot ones have a short, sweet life, blast away and then explode. The bigger it is, the more violent its death is. But the more violent its death, the more it creates. So, a big bang. It tries to burn iron. Right, so that's what happens. This lovely word, this process is endothermic. In other words, it ends it. Everything goes pear-shaped, the whole lot collapses, and we get a supernova. It's so powerful, it will outshine the billions of suns of our galaxy, and it will do it for several days. There's reports of them being seen during the day, tremendous amount. It creates a large amount of heavy elements. This is what we think is this is the latest. However, I noticed about a week ago that they were having an argument over gold and being produced by something else. But hydrogen mostly by Big Bang fusion. The green ones by dying low mass stars. The yellow ones by exploding massive stars. We've got merging neutron stars, which is probably gold. So AU, yeah. Exploding white dwarfs. So this is the theory at the moment where all the elements came from. As you can see, looking at that table, lots of things have happened before our sun even formed. So for our sun to work and for us to be here, all these suns had to blow up, create all these elements, and then get them back together. So at 15 times the sun, the mass is so great and it forms a black hole. I had a talk on a black hole, and the arguments that went on about a black hole before it was actually discovered, and they actually got a picture of it. And some of the greatest mathematicians were betting, nah, no, it's not a black hole, no such thing. These are the engines that drive the middle of the galaxy. I also, when I stirred the coffee cup, you could see all the bubbles go round, and there was a dirty great thing in the middle. And that's what it turns out to be, a black hole that drives the galaxies. And they are supermassive. There's millions of suns. So the cycle. This is basically, let's see, the easiest way to do this is to say, you know, the water cycle, i.e. it rains, rain falls down, goes down the drain, into the rivers, goes into the sea, it's heated up by the sea, forms clouds, and it rains. So it goes round and round. So hydrogen atoms make suns, right? And the very first suns were big, massive ones. Suns make more complex atoms by exploding, or just by their production. They explode, scatter their debris across space. The debris forms into gas clouds. Clouds collapse, form suns. What I'm saying is, everything you see around you was once in the heart of a supernova, including yourselves. In other words, we're all stardust. There you go. And that's a nice place to finish. So I'll call it a day there, and I'll ask for any questions. Thank you very much for listening.
Thank you for that, Sandra. It's really fascinating. Thank you very much. Can we thank Sandra for all the questions? Anyone got any questions for Sandra? Either about the talk or about the aurora that's going to happen tonight? Is there anything you want to put your name on the chat if you want to read, ask a question, or on YouTube if that's where you are? Got anything? Is there anything on YouTube, Will? At the moment?
No questions on YouTube. Fascinating talk though, Sandra. It really was very enjoyable, actually. Thank you.
While we're waiting.
You get a lot. Oh, go on.
So carry on, carry on.
No, I try to cover, if I can start some stuff, it'll be very, very complicated. But if I start simple and build it up, how people discovered things and stuff, most people can follow that, and they actually see how it works. It's like a parsec. People had no idea, why'd they use a parsec, and things like that. And it's actually a fascinating story. And the Hertzsprung-Russell diagram, I know people who actually do a talk on nothing but that, so it's extremely complex. But if you start at the beginning, build it up slowly, people then go, I understand that. I understand why they did that, how they did it, and where it got them. And I mean, now we've got, as I say, got standard candles like Wolf-Rayet stars and things like that, some supernovas. And we work out the distance of galaxies, not just stars. So it's incredible, but fascinating. Yes, go on.
I think that the idea of the parsec that's quite an interesting story because people often ask why do you not use light years? Why do professionals use parsecs? So it is quite a good story. That I mean, a light year is an interesting one because people understand that one, but it's less scientific in many ways than the parsec. So yeah, it's quite a good story, that one. Yeah.
Mm.
But
But
also
also
where
it's
the
fascinating.
sorry,
Go ahead, Peter. Yeah.
I was just going to ask where Corona Borealis fits in the range of stars.
Corona Borealis.
You mean magnitude?
Yeah, where does it fit in the diagram from small to very large?
Oh, you mean the star T Corona Borealis?
That's the one, yeah.
All right. Okay.
I'm not quite sure. Each star has, for instance, our sun is -26 apparent, but its absolute magnitude at 10 parsecs is about 4.2, I think 4.3. In other words, it's just one of the weak stars in Ursa Minor. So that's what it would look like. A lot of stars. If you look, you need a catalogue. They'll give the apparent and the absolute magnitude of stars, and they work them all out once they get the distances. I noticed when I was first doing this, and if you're used to scientific stuff, there's always a plus or minus, and some of them were plus or minus 50%. So I mean, so, but I think the with the modern day telescopes and modern day cameras, they can get very, very accurate distances now.
Well, like many
But
many other people who've just Googled T Corona Borealis, I have as well. So it's about 1.1 times the mass of the sun, about 75 times the sun's radius as well. So not very heavy, but this is presumably the red giant, the larger of the two in the system. The white dwarf will be smaller. So there we go.
does it
Can I,
say
can I
what
ask?
its absolute?
Sorry, Sandra. Can I ask Sandra what the little diagram you put up about the classification of different star types was that
Yeah.
based on that was based on the surface temperature? Is that right? Of
Surface
each
temperature
type?
and the lines. You
Uh-huh.
had the Fraunhofer lines and the surface temperature combined,
Right.
so
And
they
you
could see what was being burned, and also by the color. So
okay. And I hadn't appreciated before I saw your slide that each letter was divided into 9 sections.
yes,
Could you say a bit more about the 9 sections?
uh, basically uh, it's a way of classifying it by brightness, so and temperature. So, for instance, we're a G2, a G3 would be slightly brighter, G4, etc., etc. They'll obviously have cutoff lines if you want to look at it specifically. There'll be now definite criteria. As I say, Annie Jump Cannon was one of these girls who could look at a star and say it's one of those, and she was very clever. But now they'll probably have distinct classifications, and you'll be able to say, uh, when you look at the star, right, it's showing these Fraunhofer lines, it's got this color, its surface temperature is this, therefore it's an A and it's an A4 or something like that, So
Ah, right. Thank you. So the I presume the 1 to 9 inside each group was just brightness. So as the number gets
it was
bigger,
basically bright.
brighter.
It was basically surface temperature brightness. Yes. Yeah.
Yeah, sure. Okay. Thank you very much. That's interesting. Hadn't understood that before.
Yeah.
We've got a question from on YouTube from Troglodytes. Do we know how old the oldest star is that has been identified?
Oh, and now ages of stars. The oldest stars are going to be the brown dwarfs. They're the ones that last the longest. However, we're looking way, way back. So You'd have to dig. I'm not exactly sure what the oldest star is, but you'll have brown dwarfs that were created, which we're still going today, and they were created right at the start because they last for trillions of years. When all of the rest of us are dead and gone, and all the stars are wiped out, they'll still be going.
Fantastic.
But they are very difficult to see because we we rely on our eyes and what we see. I mean, this dark energy, dark matter stuff. It may be that there's just a whole load of stuff that we just can't see. Um, and it's very, very cold and things, but they're large lumps. So we'll have to see as we get better at it, as the James Webb starts digging in for infrared and things like that, we might be able to figure out what's going on. At the moment, I find it fascinating because there's something new every time, so it's great
Absolutely.
fun.
No, that's a great way of putting it, actually, that this dark matter and stuff, that I suppose the least energetic things are the longest living kind of stuff. So it's
Yeah.
incredible. It's great. Thank you very much, Sandra.
Does that mean if I sit about on the couch and eat chocolate, I'll live longer?
That's exactly
I like that. Yeah. Don't forget your beer or your wine.
Any more questions, Sandra? If not, maybe you should tell us a bit what we should expect tonight with this strong signal for the aurora, Sandra.
I tell you what, I'm still sharing screen, so hold on a minute. Where are we? What's that one? Oh, I'll see if I can. Uh,
Those of you who didn't hear, there's a very strong aurora alert on sun. I think it's going to be quite a good one tonight. So once it gets dark, go look to the north.
right, all right. Here we go. There you go. There's the latest oval. Right down the UK. That's going to be visible in London.
All right, very strong.
That's at the moment. Let's see.
So even with the moon as bright as it is, we should still see that, I think.
I would say so. Yes. Yeah. It'll depend how lively it is. It kicked off at 4 o'clock. So normally when it starts off, it's lively but it has a habit of calming down after a while. But we'll see. The other thing I'd ask you if you go at the aurora, don't just look north, look south, look east, look west, because you might see Steve or star arcs and stuff like that. So any reports, please send them. Yeah. Keeps me busy, but it keeps me off my toes. So
That's great.
so that's the state of play at the moment. Let's see, what's that the date? At 2014. That's only about 10 minutes ago. So
Sandra, you mentioned there were no stupid questions in astronomy. I'm just about to ask a stupid question.
this
Why why is the I hadn't I'm unless I genuinely don't know, why is the aurora donut shaped like that? Why does it have a hole over the actual pole?
my guess is this is black aurora, i.e., if the aurora really worked as it should, right, we'd all be fried, right? We'd be in a microwave. Because you're talking, let's see, normally somewhere around here. Now, have they got it? Here we go. That's 98.6 gigawatts coming in an hour. It's enough to start cooking. And what happens is it escapes out of the poles. You get these polar jets. You get the same thing in formation of stars, just as the stars form. You get jets out from the magnetic north and south. So that hole seems to be a standard one. And so the Earth keeps a balance, if you like. If it didn't, we'd be in trouble. We really would. You wouldn't look like that. I wouldn't look like that. We'd probably look like cockroaches because we'd need the armor to protect us from the radiation. But no, it works basically as a blast escape hole. You see bits of black aurora every now and then, and it basically looks just like a gap, a hole, and it's exactly the same thing. It's the electrons going straight out into space and back into the solar wind, down the tail, etc., etc. We always used to think that this came in straight, but it appears to be now that when the electrons strike it, i.e. the solar wind strikes the Earth's magnetic field, it rattles the tail, and it's the rattling of the tail that sends the electrons crashing down into the poles. And that's the magnetic field bit where it's strongest, where it's very, very, very weak. It can actually escape from there. So that's basically it. You're basically looking at a magnetic field with a sort of gap in the middle.
Well, the only thing I can say to your answer is wow. Thank you very much.
We're learning bits all the time. You've also got the Van Allen belts as well. So that's where you got Steve. You've then got the rotation of the Earth, and we've only just recently discovered that that's if you're at the back end of a ship, the curvy bit, you can see turbulence, can't you? And little circles of turbulence. That's what causes picket fences, and they actually are parallel. They're not vertical; they're parallel like that, and they're about 300 kilometers, and it's just caused by the turbulence of the Earth moving through, and the turbulence on the magnetic field. That pressure there is caused by the sun, so it forces it across to the other side. So you'll always see a sort of almost donut shaped slide with a flat bit there from where the sun is. So the sun is probably just about there, California. Oh, very nice.
Well, again, wow, that's interesting. I hadn't appreciated that. I had just kind of
Oh,
assumed that it was just a different shape randomly, but that's very
no,
interesting.
no, it's the pressure of the sun, and
Wow. Thank you very much. That's superb. That's great. Thank you.
oh, you're more
Yeah,
than welcome. You're more than welcome.
the app I'm looking at has got a chance of seeing the aurora as far south as Liverpool today.
Mm-hmm.
Oh, I would go further than that. This is just a rough guide. If you can see it there, if it goes down to there, you could probably see it from Calais
All right.
or the Cherbourg Peninsula. I would say it would go just a fraction further.
I'll let you know if it's around the Dordogne in France, but I don't think it will get down that far.
You never know. Hold on a minute. Let's see if I can. I've got so many tabs up. Let's see, is that the one? This is going to be difficult, I think. Here we go. Let's have a look at Disco. This is a deep space climate observer I'm going to wind in. And basically, this is at Lagrange point 1. Yeah. Oh, look at that. Here we are. There it is, kicking off at about 4 o'clock, swinging south, way, way, way. And then just as it's going to go dark, it's going to go north again. Look at that. Now, I don't know if it's suddenly going to go south again. This is where it's totally unpredictable. But it's this bit way south of this line tells you that it's going to be very, very powerful. It may last for a bit longer, but I've still got bright light outside. I've still got to put the hens to bed yet, so they'll be still clucking around in the night. But you get the idea. this long negative field. And if I look at the dashboards, it should give you the levels. There you go. You got G1. There you go. So we got a level 4, 4, 5. So yeah, it's a good one at the moment. But like I say, it's still light up here. So
Yeah, still light here
the
as well.
Europeans will be in.
It is clear here, so despite what Graham
Yes.
said, yes, yeah.
Yeah, I think I've got pretty clear sky up there at the moment, so it's not too bad. But
Well, that's great. Thank you very much for that, Sandra. I know in the past our society had quite a lot of involvement in aurora watching with Dave Gravine, Ron Livesey, and so on. Maybe it's time to start up another project for us. Fran Goodman, you're the arch aurora hunter in our society. Fancy running an aurora project and communicating with Sandra and so on? That'd be something that would be good. Although Edinburgh's not the best place for it, but in East Lothian's pretty good, I'm sure. Okay, well, thank you again for that, Sandra, and we'll all go out and look for the aurora later on. So coming, thanks, Sandra, again. Thank you.
it was a great pleasure talking to you all, and thank you very much for being a super audience.
Okay, well, we have one more thing to do, which is to announce the image of the quarter competition winner. So I'm just going to take over control here. Hopefully you can see that.
Yeah.
You'll see that, okay? Yeah.
Like that one.
Yeah.
So this is the Imagery Quarter competition from January to March 2024. We're just taking in that. The judge is David Harvey, who won the Image of the Year competition with that wonderful picture of the Horsehead Nebula. So I'm just going to go through all the entries briefly that were put in. There was 19 entries. If I haven't got your entries here, I do apologize. I did check my email quite carefully, but if it didn't get to the right email, then it may not have got in here, in which case just blame David. That's fine. So hopefully David will say why he chose the image he did. So first one we have this was the only one from using data from our Azaro observatory from John Briggs M101. You were allowed to use it this time, but maybe different criteria will be used for judging that. I don't really know from David. This is a beautiful picture of the Milky Way taken from Australia by Frank Goodman, which was down there, or the emu. David Brett from Edinburgh with less easy skies probably took this wonderful picture of the Crab Nebula. I'm not going to read all the details, but you can. I'll put them online in the newsletter at the end of the week. David also took this picture of the Hamburger Galaxy after it was mentioned at the AAC meeting. Lots of detail in the dust. David also did a full panel mosaic of the sun. If you look at that, there's quite a lot of detail in that. It doesn't show up very well on here, but there was a lot of detail in there. Mike Christie took this picture of the Rosette Nebula. Very nice winter target. He also took this picture of the moon. You can see Plato and the Alpine Valley and the Apennines and the Alps. Ron Morley took this picture of M42, the Orion Nebula. Ron's in Fife, so a slightly better skies probably over there.
You still needed.
Yeah. Oh,
No, you're not muted, David. I'll mute you. Then Ron took this picture of the Bubble Nebula. And this is Ron's picture of the Solar Edge Prominence, or the Ring of Fire, as he calls it. Lots of nice detail around the edge there. Nigel, also from Australia, took this picture of M83, took his Sea Star as luggage. It survived intact, which is good to know. Diggy Smart went down to Taller Reservoir in the Borders and took this nice wide-angle image of Orion constellation it surrounds with the reservoir bridge there. And in the East Calder, just around the road from me, he took this picture of the Orion Nebula itself. Ian Smith, using his brand new Super Duper Bazooka telescope, took this picture of the M82 Cigar Galaxy. Ian's in East Lothian, so he gets better skies there as well. So he should definitely be marked down for having good skies. And this picture of the Jellyfish Nebula. I suspect that wasn't with the RC, probably with your wide-angle scope. And he also has the Tadpoles and Flaming Star Nebulae as well. Eros Tang, who does image from the centre of Edinburgh, get some amazing pictures, has this picture of the Popped Balloon Nebula, or it says the Garlic Bulb Nebula. I didn't know it was called that as well, but certainly looks like a popped balloon. And Eros also had a picture of the Soul Nebula. And the final one from Eros here is the Tadpoles Nebula. All these pictures are on our Flickr group, so you can see them all there in more detail. Pat Devine took this picture of the Christmas tree cluster. It has the Cone Nebula in there as well, and the Foxfur Nebula, which I always think looks like the Rat Head Nebula. It should be a rat's head, not a fox fur. David, over to you.
Aha. Yeah, right. Well, it's like I liked them all. As I said, I wrote to you, didn't I? Saying this is a fantastic task, but it's very daunting. And I looked and I thought, oh, looking at them during the day, I know from my own experience, looking at my processing when I'm doing pictures, wait till the evening and look in the dark, and it looks even, you can see different things. So I started looking at them in the night time as well. And as I say, I looking at them again now as you're flicking through, I'm thinking, have I made the right choice? My mind, I was thinking, because I've got the Sky and Telescope magazine's calendar here, and I was looking just at the back of it where they have all the images for the month, and I was thinking, is there anything there within hours that would complement that? And equally, I was thinking, something that would be a wow on a book cover, calendar, even I said, like I said to you, a sci-fi movie or something, but realistic. And obviously, I thought it'd be good if it did come from someone's back garden, which I'm passionate about myself. So, and also the one that I was a little bit jealous of, because I don't do this sort of thing. Well, I should, and it's inspired me to do it. So the winner is, ta-da!
Don't cover your eyes, Ron. Ron Morley with his Ring of Fire. Well done, Ron. Thank you, David.
Good God. I'm speechless.
Don't worry, the prize isn't worth that much, but it's the immortality of the prize that matters.
It's when you flick through 19 different images, after a while, you keep going back to one particular one, don't you? Or something, and that was it.
Yes, I was quite pleased with this one, the way it came out. It's I'm just learning how to do solar hydrogen alpha astronomy, and this sort of popped out. It didn't have much processing at all, so it's not fiddled. And it's just with a 50mm hydrogen alpha scope, and yeah, it came out quite nice. And I made it red really to make it look like what the eye sees. Yeah, so gosh, it's different. I'm just a bit in awe of the other ones with the deep sky detail. That's what I'm trying to do. But yes, wow, thank you, Dave.
Right.
Where was it taken, Ron?
It was taken from my patio. Just taken in the front garden. Let's get this right. No, it was just taken in the back garden, actually. Yeah. Yes, it's just they're all taken from the sun. The sun. I think it was Between the Clouds, 25-second video with the Lunt 50, the 600 nanometer filter. And what else? The camera is just one of these Altair 130s, so it's quite a modest camera. And actually, the detail's better. This looks a bit blocky on my image here, but it's better than what it looks on the screen.
They call flicker, yeah.
Yeah, it all comes out
pretty good on Zoom, though.
That's always a problem with the flicker, WhatsApp in particular.
Yeah.
But, I tried popping on a 5x Barlow, and the definition began to go. So I've got something to work on as well. But wow, gosh, thank you very much.
Yeah, well, someone will be in touch with you about the prize. If they don't, get in touch because they ought to. So the next image of the quarter competition is now active from April to June, and as I've said in the past, it doesn't just need to be a picture. Get creative. It could be a graphic, it could be a video, maybe it's an infographic or something like that, or a mosaic, or just something a little different. And if you want it before, maybe the next judge, which is Ron, will demand higher standards of you, so do something a little bit different as well. So you've got 3 months to be nice to Ron if you want to win the next competition. That's the way it goes here. Bribes are always accepted, I believe. Okay, I think that's it for this evening. Thanks again to Sandra and everyone who's taking part, and we'll see you at the next meeting in May. Okay, good night.
Good night, everyone. Thank you.
Good night.
Good night.
Good night, all.
Good night.
Good night.
Good night. Good night.
Thank you.
Thanks, Sandra. Thank you very much.
Yeah. Cheers, Sandra.
Oh, you're
Cheers,
more than
everybody.
welcome.
Good night.
Bye.